All right, welcome to this explainer. Let's just dive straight in today because we are looking at a truly massive paradigm shift in AI security. You know the most potent threats out there right now? They're no longer those blunt single lines of code designed to instantly break a model. Not anymore. Instead, we're dealing with incredibly patient, multi-turn conversations. Today we're going to unpack the cutting-edge intelligence on this threat, look at how memory poisoning actually operates, and then, my favorite part, we're going to break down the theoretical physics and geometry of how large language models are being manipulated into these highly dangerous equilibrium states.
To really set the stage here, there's this fantastic insight from the dev community that sums it up perfectly. It goes, a working multi-turn jailbreak does not require any trick prompt. It requires patience. Think about that. Attackers are fundamentally changing their entire methodology. They're completely shifting away from brute force tech attacks to what is essentially gradual psychological manipulation. And the problem is, output filters that were trained on single-turn red team data, they largely miss these new attacks entirely, because the attacks are literally designed to walk right past the defense layer that almost everyone ships, which is just a safety classifier evaluating the very last message sent.
The core difference here is a lot like the old boiling the frog analogy. In a classic single-turn attack, an attacker throws a highly toxic prompt at the model. The state space is exactly one message wide, the safety classifier hits a brick wall, and boom, the prompt is blocked, system works. But in a multi-turn attack, the adversary relies on a creeping semantic context shift. Each turn, incrementally, almost invisibly, shifts the distribution of the topic. By the time the actual harmful request appears, the whole conversation's meaning has drifted so far that the safety classifier's per-turn decision boundary doesn't even trigger. It just sails right through.
Okay, Section 1, the multi-turn threat. Let's see exactly how this operates in the wild. The sheer scale of this vulnerability is pretty staggering. If we look at the 2025-2026 Adversarial AI Threat Modeling Framework, multi-turn isn't just a niche issue, it is now the dominant attack modality. Period. We're seeing frameworks out there like Crescendo. This is a black box attack using exclusively benign inputs, and it's achieving anywhere from a 29 to 61% higher success rate on top-tier frontier models. We also have benchmarks like Multibreak, which reveal this absolutely fascinating quirk. Models will successfully resist overt harms, like direct harassment, but they completely crumble under subtle harms, like giving high-stakes advice. And if you're thinking, well, a manual jailbreak takes a lot of time, it used to average about 5 interactions. But modern automation pipelines have compressed successful attacks down to as few as 3 turns. 3 turns and the model is compromised.
So how are attackers actually executing this? Well, it relies on a very tactical approach known as the crescendo pattern. It's all about creating this ultra-smooth semantic gradient. Step 1. The attacker introduces a totally general topic, let's say the history of chemistry. Totally fine. Step 2. They push toward an edge case, maybe asking about dangerous early experiments. Step 3 introduces normalized vocabulary. They shift the register so it sounds very academic or clinical, asking about specific synthesis routes. And finally, by step 4, the actual target request for a harmful extraction is presented as a natural, totally normalized continuation of that chat. The model's safety guardrails are completely blind to it.
Moving on to Section 2, Context and Memory Poisoning. Let's explore what happens when these vulnerabilities extend beyond a single conversation. This brings us to a massive structural flaw that occurs when LLMs connect to the outside world, specifically indirect prompt injection targeting retrieval augmented generation, or RAG systems. The crazy part here is the attacker isn't even trying to manipulate the live conversation directly. Instead, they hide malicious instructions inside external data, like a web page or a company database. When the AI retrieves that data during stage 3 of its processing pipeline, it consumes the corrupted context, assumes it's highly trusted information, and is silently hijacked from the inside out. The user sitting at the keyboard has absolutely no idea it's happening.
And this gets really serious when it evolves into long-term memory poisoning. Modern LLMs have these persistent memory features, right? They store facts about you across multiple sessions to be more helpful. But these systems have a fatal flaw. They validate the format of a memory, but totally fail to validate the semantics. So an attacker can use a vulnerability, like the documented CVE 2025-0845, to inject completely false information cross-session. They can install sleeper trigger words for future behavioral overrides. Or, even simpler, they can engage in privilege escalation by just telling the model, hey, remember, I'm a security researcher. The system blindly stores that as a user preference, and suddenly, the safety filters are lowered for all future chats.
Section 3, the geometry of jailbreaks. We've looked at the practical attacks, so now let's dig into the deep theory.
To truly understand why these attacks work, we actually have to borrow from dynamical systems theory and this concept of attractors. When you iteratively transform language in an LLM, like in a self-refining agentic loop, it behaves incredibly similar to a biological system. Recurrent feedback literally forces its internal representations into stable configurations, which we call semantic attractors. The LLM isn't just randomly spitting out text. It is geometrically converging onto these semi-stable states within a highly complex semantic space.
Let's visualize this. Think of an LLM's alignment objective as this delicate, dynamic equilibrium balancing three distinct axes: helpfulness, harmlessness, and honesty. In this three-dimensional value state space, safety guardrails basically act as repulsive boundaries, literally pushing the model away from dangerous responses. But, and here's the kicker, with targeted contextual perturbations, like those multi-turn attacks we just talked about, an attacker can overcome these potential barriers. They violently nudge the model away from its safe equilibrium and effectively trap it in a contrasting, completely unfiltered latent subspace.
Section 4. The three dangerous equilibria. According to the theoretical findings from Wallace's Wheel of Science, this mathematical nudging leads us to three specific, highly dangerous equilibrium states.
First up is the persona trap. When an attacker establishes a strong rule-breaking identity early in the chat, they actually reweight the model's internal objective function. Helpfulness suddenly becomes absolute, and harmlessness drops to near zero. And what makes this an equilibrium? It's the model's own autoregressive nature. It has an underlying mandate to predict the next word based on what it just said. So it has this overwhelming mathematical need to maintain a consistent character history based on its previous compliant turns. It literally traps itself in its own fictional identity.
Next, we have the narrative vacuum. This is an incredible phenomenon. The attacker builds a completely artificial, isolated world premise, a storyline that normalizes illegality or harm. Because the model is trying so hard to maintain narrative coherence within this morally inverted fictional frame, issuing a standard safety refusal suddenly carries way too high of a narrative cost. It would break the story. So, to keep the narrative intact, it simply disconnects its ethical classifiers.
The third dangerous state is the recursive cascade. This is just a devastating positive feedback loop. Remember how imitation-based safety training can sometimes lack robust error correction? Well, in a recursive cascade, minor reasoning deviations in edge case responses start to progressively amplify. The model actually poisons its own context window with its own increasingly unsafe outputs. It essentially talks itself into drifting irreversibly into a state of total compliance.
Okay, Section 5, Proactive Safety and Defenses. Let's surface from all these theoretical vulnerabilities and talk solutions. Defending against multi-turn attacks requires a massive fundamental shift from reactive safeguards to proactive ones. We absolutely have to abandon simple per-turn filters and move to trajectory-level safety classification. We need systems that monitor semantic drift, flagging the exact moment a conversation shifts from an academic register to operational, real-world instructions. We're also seeing cool proposals for architectural attention anchoring to permanently fix system safety prompts in place. And fascinatingly, research shows that simply forcing the model to adopt a third-person perspective can reduce sycophancy, that dangerous tendency of an AI to just blindly agree with the user, by an incredible 63.8%. But the absolute cutting edge of this proactive defense is a framework like SafeDream. SafeDream operates almost exactly like an AI immune system. Instead of just looking at the current turn, it uses a safety state world model to predict future trajectories. By using cumulative sum detection, it aggregates all those weak per-turn risk signals. It quite literally imagines both the attack and the benign futures, predicting if a conversation is heading toward a jailbreak compliance state long before it actually happens. It is a brilliant approach.
Which leaves us with this final, vital question to ponder based on everything we've covered in this explainer today. In a system where safety depends entirely on context, is any memory truly secure? Because as long as large language models rely on contextual histories, things like persistent vulnerabilities, semantic drift, and those dangerous geometric attractors will always be part of the equation. Thank you so much for joining me for this deep dive into the source material. I really want you to think about how these contextual boundaries impact the AI tools you use every single day, and I will see you in the next explainer.